Hi guys, I'm Meena. Today's topic is about interaction of radiation with matter. I am currently studying in Sri Venkateswara College of Engineering, pursuing my bachelor's in computer science with the specialization of cybersecurity. Let's get into the topic. Today, we'll learn about different process of radiation and energy density expressed in terms of Einstein's coefficient. Coming to the introduction, laser is an acronym of light amplification and stimulated emission of radiation. Radiation is the emission and transmission of energy in the form of electromagnetic waves or particles. It can be categorized into two main types. First is ionizing radiation and second is non-ionizing radiation. Example of ionizing radiation includes X-ray. An example of non-ionizing radiation includes microwaves. When radiation interacts with matter, several processes can occur, depending on the type of radiation and properties of the material. Some key interactions include the first one is absorption, the process in which the energy of the incident radiation is taken up by the material, increasing the internal energy of its atom or molecule is called absorption. Second is scattering. Radiation may change direction upon interaction with matter without losing energy. This is common with non-ionizing radiation like visible light scattering off a rough surface causing diffuse reflection. Third is ionization. Ionizing radiation can transfer sufficient energy to atoms or molecules to remove one or more electrons. Fourth is excitation. Electromagnetic radiation can also raise an electron to high level without ionizing the atom. This temporary excited state can lead to further energy release. Now let's learn about different process of radiation. A laser is a highly monochromatic coherent beam of light of very high intensity. In 1960, Mainman built the first laser using ruby as the active medium. The radiation interacts with matter in three different type process known as first is induced absorption, second is spontaneous emission, third is stimulated emission. Let's know about the first one, which is induced absorption. Let us consider an isolated homogeneous atomic sample which is placed in a monochromatic radiation such that the energy of each photon is equal to the difference between energy state of first and the second energy state. When the right energy strikes to the atom in the ground state, then the electrons of the atom absorbs the photon and it is excited to the higher energy state. This mechanism is known as induced absorption. Here we can know that when an atom in the ground state, say that E1 absorbs a photon of energy, E2 minus E1, it makes the transition into the excited state E2. When a photon and an atom is combined together, you will get a new form of atom. In the figure, we can know that when the photon is strike to the ground level of the atom, then the electron in the ground state is excited to the higher energy state of E2. Therefore, the rate of induced absorption depends on the number of atoms present in the ground state and the energy density of the radiation field. That is, rate of induced absorption is directly proportional to the N1 E mu. Coming to the second one, spontaneous emission. The atom in the higher excited state cannot remain permanently due to the excitation violates instability condition. If two atoms are in the same excited state and return to some lower energy state, two photons having the same energy are emitted. These two photons may not travel in the same direction. They produce incoherent beams of light. The excited atom, after a short duration of about 10 power minus 8 second, automatically jumps back to its original state, emitting the energy H mu. Spontaneous emission can be represented like when we consider an atom in excited state E2 and the excited state of an atom is highly unstable, within a short interval of time of the order, the atom returns to its lower energy state, say E1, and emits a difference in energy in the form of photon of energy h mu is equal to E2 minus E1 spontaneously. According to the figure, before emission, the atom is in the higher excited state. Then, without applying any energy, it comes back to the lower energy state and emits the energy. The rate of spontaneous emission is dependent on the number of atoms present in the excited energy state. That is, rate of spontaneous emission is directly proportional to N2. Coming to the third one, stimulated emission. In this process, when a photon of right energy strikes an atom in the excited state, the photon stimulates the atom to come back to its original state by releasing another photon of energy h mu, which is absorbed earlier. Let us consider an atom in the excited state E2. If a photon of energy E2 minus E1 is made to an incident on the atom in the excited state E2, the incident photon forces the atom in the excited state to make the transition into ground state E1 by emitting a difference in energy in the form of a photon. Now let us consider two conditions, before emission and after stimulated emission. In the before emission, we can see that atom is in its higher excited state, and when the right energy of photon is applied strikes on the atom, then the electrons of the atom absorbs the photon and comes back to the ground state by releasing two forms of energy, and the rate of stimulated emission depends on the number density of atoms in an excited state and the energy density of the radiation field. That is, the rate of stimulated emission is directly proportional to N2 E mu. Now let's learn about energy density expression in terms of Einstein's coefficient. Let's derive Einstein's coefficient. Let N1 be the number of atoms per unit volume in the ground state E1, and these atoms exist in the radiation field of photons of energy E2 minus E1 is equal to h mu, such that the energy density of field is E. First one is Einstein coefficient of stimulated absorption. Let R1 be the rate of absorption of light by E1, which the atom is transformed to E2. This process is known as induced absorption, or the atom from the ground state is excited to the higher excited state. The rate of induced absorption is R1 is directly proportional to N1 E mu, or R1 is equal to B12 N1 E mu, where B12 is known as Einstein's coefficient of induced absorption, that it represents the probability absorption of the radiation. Energy density E is defined as the incident energy of an atom as per unit volume in a state. Second is Einstein's coefficient of spontaneous emission. Now, atoms in the higher energy level E2 can fall to the ground state E1 automatically after 10 power minus 8 seconds by the process called spontaneous emission. The rate R2 of spontaneous emission E2, which is from the higher excited state falls to the ground state, is independent of energy density E of the radiation field. R2 is proportional to N2, or R2 is equal to A21 N2, which is second equation, where A21 is known as Einstein's coefficient for spontaneous emission and it represents the probability of spontaneous emission. Third is Einstein's coefficient of stimulated emission. Atoms can also fall back to its ground state E1 under the influence of electromagnetic field of an incident photon of energy E2 minus E1 is equal to h mu by the process called stimulated emission. Rate R 3 for stimulated emission, E2, which is higher excited state of the atom, come back to the lower excited state, which is directly proportional to energy density E of the radiation field, and R3 is directly proportional to N2E, or R3 is equal to B12 N2E, where B12 is known as Einstein's coefficient for stimulated emission and it represents the probability of stimulated energy. Now let's derive the derivation by using the relation of Einstein's coefficient of three states. In steady state at thermal equilibrium, the two emission rates, spontaneous and stimulated, must balance in the rate of absorption. Thus, R1 is equal to R2 plus R3. Using three equation, which was induced absorption, stimulated emission and spontaneous emission, we get N1B12E is equal to N2A21 plus N2B21E, which is equal to N1A21 by N2B21 into N1B12 by N2B21 minus 1. By taking common out N2B21 from the denominator, we get E is equal to A21 by B21 into 1 by N1 by N2 into B12 by B21 minus 1. Einstein proved thermodynamically that the probability of stimulated absorption is equal to the probability of stimulated emission. Thus, B12 is equal to B21. Then equation 4 becomes E is equals to A21 by B21 into 1 by N1 by N2 minus 1. From Boltzmann distribution law, the ratio of populations of two levels at temperature is expressed as N1 by N2 is equal to E power E2 minus E1 by KT. N1 by then further N1 by N2 is equal to E2 minus E1 can be written as H mu by KT. Now, according to Planck's radiation law, the energy density of the black body radiation of frequency V at temperature T is given as E is equals to 8 by H mu cube by C cube into 1 by E power H mu by KT. By comparing equation 6 and 7, we get A21 by B21 is equal to 8 by H mu cube by C cube. This is the relation between Einstein's coefficient in laser. Now let's know about the significance of Einstein coefficient relation. This shows the ratio of Einstein's coefficient of a spontaneous emission to Einstein's coefficient of stimulated absorption is proportional to the cube of the frequency V. It means at the thermal equilibrium, the probability of spontaneous emission increases rapidly with the energy difference between two states. Now, quickly let's recap what we have learned today. We have learned three forms of radiations of matters. First is induced absorption. The atom in the ground state, when the right energy strikes to the ground state of an atom, then the electrons of the atom absorbs the photon and it is excited to the higher energy state. This process is known as induced absorption. And second one is spontaneous emission. The atom in the higher energy state cannot remain permanently due to the exploitation of violation of the stability condition. So it comes back to the ground state by releasing an energy. And then coming to the third one, stimulated emission, the atom in the higher excited state requires an energy which strikes the atom, and then the atom comes back to the ground state by releasing two forms of energy which was absorbed earlier. Thank you for watching my video. Hope this was informational and please do like, share, subscribe to my channel.